Welcome. This video is going to talk about factors that will affect your reaction rate. And these are factors that can both speed up or slow down your reaction rate. And all factors rely on affecting the collisions, either the number of collisions or the energy of the collisions, or even the orientation of the collisions. You have to affect one of those three requirements if you're going to affect the reaction rate. And so that's what we'll be concentrating on here as we look at these different factors. And then also I want to point out that it's just as often that we're looking at speeding up a reaction as we're looking at slowing down a reaction. In the case of food, we often want to slow down the reaction rate to keep it longer, give it what we call a longer shelf life so it doesn't start decomposing or going bad more quickly. With diseases, if we can't find a cure for a disease, then if we can slow it down, slow down its progress, that also can extend quality of life. So, when we talk about affecting reaction rate, don't just assume we only want to speed up reaction rates, although that's often the case too. So, these first four are pretty straightforward and probably ones that you could have guessed, at least three of these maybe you would have guessed if asked to come up with ideas on how you could change the reaction rate. The first one is simply called the nature of the reactants. And that simply means it depends on the substances you're using. More reactive elements have faster reaction rates. Remember, over in family 1A, those are the really reactive metals. They're the largest. They only have one valence electron. It's way out there, easy to pick or take away. 7A, they're the smallest. They have the highest electronegativities. They have 7 valence electrons. So looking to pick one up. So if you want to increase your reaction rate and you can substitute a more reactive metal or more reactive nonmetal and get the same product you're looking for, then that would be one way to speed up your reaction rate. The second one is concentration. And concentration, remember, isn't the same as volume. And this is where people get confused. So using more of the same stuff isn't going to speed up your reaction rate. It's just going to give you more reactant and eventually more product. But concentration is how crowded the particles are in there. So if you go from a 1 molar concentration to a 2 molar concentration, that means you have twice as many particles in the same space in that 1 liter of solution. So more particles are going to mean you have a greater chance of a collision and you should have a faster reaction rate. Surface area is just the difference between having like a sugar cube versus having a teaspoon of sugar that you put in. So surface area means that more particles are going to be exposed or available for collisions. So the more you powder or finer you make that reactant, and this is talking about solids, then the faster your reaction rate will be. And then finally, temperature. An increase in temperature is going to not only increase the number of collisions, it's also going to increase the energy of the collisions. So temperatures really has a double effect on your reaction rate. And in fact, it's estimated for most reactions, a 10-degree increase in temperature will double your reaction rate. So temperature is definitely an easy way to increase your reaction rate. And before we discuss the last two factors, we need to talk a little more in depth about this idea of activation energy. Remember, it's the minimum amount of energy needed when the reactants collide to form the product. It's abbreviated as E sub A. And so a higher activation energy is going to decrease the chances of product forming, which means the reaction rate will be slower. And then the converse, a lower activation energy will increase the chances of product forming. So some reactions have a very high activation energy, others have a low activation energy. Has nothing to do with its endothermic or exothermic. But you could change the amount of activation energy. So the first four we looked at all have to do with increasing the number of collisions. These last two ideas actually revolve around changing the requirement, changing the energy. So think about, if someone's doing a high jump, you're going over the bar. If you lower the bar, more people are going to be able to succeed at that. If you raise the bar, fewer people are going to be able to do that. Another analogy I'd give you is with a test. If I change the curve, if I lower the curve, you didn't change your score, you didn't do anything different, but suddenly your grade improves. Or, on the other hand, if I raise the curve, again, you didn't do anything different, but your grade has dropped. So here's a couple graphs showing that, and hopefully these graphs look familiar to you. These show the progress of a reaction in contrast to the potential energy. And so here they're showing you the energy of the reactant starting, the energy of the products at the end, and then this is the energy during the transition state. So remember, this is where the bond breaking occurs. This is where the bond making occurs. Over here at the end, this is your difference in the energy of your products and reactants, and you see that the delta H for the reaction is going to be positive because energy went in. This is endothermic. So this is all stuff we've talked about. Well, the different thing that we're going to talk about here now is here's your activation energy. This is how much energy you have to, well, actually for the reactant side, here's your activation energy for your forward reaction. This is how much energy you have to put in when the reaction is going forward. This is how much energy you have to put in when the reaction is going in reverse. So when we talk about a catalyst, what we're talking about doing is we're talking about bringing this hill down and making it easier. And with something called an inhibitor, we're talking about raising the hill up. Graphic here just to show you that it doesn't matter if it's endothermic or exothermic. This time your reactants have more energy, your products have less. So this is exothermic and energy is being released. But again, there's an activation energy for the forward reaction and there's an activation energy for the reverse reaction. So catalysts and inhibitors, what do? Well, catalysts are chemicals that increase the activation or that increase the reaction rate by lowering the activation energy needed. So again, it's not going to change the number of collisions, but it is going to change the number of successful collisions. And you know of catalysts in your body because we call them enzymes. And we need enzymes to speed up hundreds of reactions in our body so our cells don't die waiting for our body to carry out the process on its own. Inhibitors, on the other hand, are chemicals that are going to decrease the reaction rate by increasing the activation energy, or in some cases, totally blocking the reaction, so fewer collisions will be successful. So this is commonly used, like I said, in food preservations or preservatives to increase the shelf life. And both catalysts and inhibitors are used often in pharmaceuticals. Catalysts are used when you're trying to stop a disease, when it's actually a medication that's going to cure you, speed up how quickly the medicine gets to the cells that need it. Whereas inhibitors are when we can't actually cure the disease, but we can slow it down and block its progress. And again, both of these work off the idea of changing that line and either making it higher with an inhibitor or making it lower. And then the last thing to mention is this idea of homogeneous and heterogeneous catalysts. And this is really a pretty simple idea. A homogeneous catalyst is a catalyst in the same state of the matter as the reaction it's catalyzing. So for example, electrolysis of water, you run electricity through water, it breaks down into hydrogen and oxygen gas. That's very slow without a catalyst. So sulfuric acid is often the catalyst added to that. Water, sulfuric acid, both liquids, that's a homogeneous catalyst. Heterogeneous catalyst is a catalyst in a different state of matter than that of the reaction it's catalyzing. So an example of this is hydrogen peroxide decomposes into water and oxygen on its own, but it's a somewhat slow reaction if you're actually sitting and watching it. So if you add powdered yeast, which is a solid, you will see that reaction speed up greatly, which now is a heterogeneous catalyst because you've put a solid in a liquid as the catalyst.